Welcome back. So the great thing with React is that it's not just a view layer, but it makes everyone rethink how you build applications. And one of the fundamental things that is now being pushed was, so before it was like mutability and object.observe and all of this. And we're now trying to get a sense that immutability is actually a very good paradigm. So Lee Byron is going to talk about it.
You guys hear me okay? I am so psyched to be here. I can't even express how excited I am. So my name is Lee Byron. I work at Facebook. I make things here, including React, GraphQL, and Immutable. And the reason I'm so excited is like the stuff that I've gotten to work on over the last 3 years is finally, you guys get to see it. So pumped. So Immutable.js, I know some of you know about this library, but for those who don't, here's the URL where you can go check this out. This is a library that I open sourced a couple months ago. And it's a library that has a bunch of immutable collections for JavaScript, like lists and maps. And it's a young project. There's still a lot of work to do. But I've been super thrilled with your response, like the community's response to this. Originally, it was like my academic project. I thought it was going to be fun to build. But I immediately, just like a Hacker News article, like 2 hours after I open sourced it, I had this huge outpouring of support for people like, man, I was waiting for the day when someone would do this with an idiomatic JavaScript API. I can read the source. This looks so cool. I'm glad that more people are pushing this idea. And with every pull request, with every GitHub issue, every time I get pinged on IRC, I get pumped up, and I just want to keep working on this project. So I'm going to talk about immutable data in general. I'm going to use some examples from Immutable.js, but everything I'm talking today is not about my library. It's about the concept. And I'm going to go through things in a bit of a weird order, but mostly because I want to show you guys a lot of code today. So first, I'm going to show you how these things actually work. And then we're going to talk about why we want to use them. And in particular, the patterns that we can use with React and Flux. So the name for these things is persistent immutable data structures. So what are these exactly? Well, immutable means that once you've created one, you can never change it again. It's done. Persistent, that doesn't have anything to do with like writing to a disk or anything like that. It means we can have a mutative API, but every time we call one of these mutative API methods, like add or push or set, it'll leave the original unchanged and it'll return a new version of that same collection. So here's an example from Immutable.js that does just this. Right here, we're going to create a list of 3 elements, 1, 2, 3, and then we're going to push on 4. And you can see that actually returns a new list. The original list was unchanged, and these are, in fact, different objects. If you equate them, they're false. That's what persistence means. So you might think, like, OK, how does push work? Well, it's implemented like this. First, you make a copy. Then you edit the copy. And then you return the copy. So you never edit the original. You only ever edit the copy. So you might be thinking, isn't that going to be really slow? Not necessarily. And I actually think React has a really good parallel to this that we all actually understand. Conceptually, when we change something in React, we re-render the entire UI. And while a naive implementation of this could be dog slow and totally impractical, we know that by reconciling the virtual DOM, that this ends up actually being really performant. So this is a matter of interface versus implementation. We can present an interface that gives you the concept of getting a new copy with the mutation applied every time you call these methods. But under the hood, we can implement them to be very efficient, both CPU time and memory footprint. This is an example from Mori, David Nolan's library, which exports the really awesome, well-tuned versions of these same structures from ClojureScript. And yes, it's slower. It is slower than mutating a mutable object. Not surprising. But it is a fixed size slower. And the day when you can say, it's too slow for me, I'm going to force you to tell me why the push operation is the bottleneck in your application. It's not. This is really damn close to native performance. Like, this is the difference between like 3 versions old Safari. But let's talk about the implementation. How do these things actually work? They work via a property called structural sharing. When we make a new one of these things, we want to recycle as much of the old one as we possibly can. Doing that means less work, right? Less copying, but it also means less memory. The structure that makes this possible is called a directed acyclic graph, or the DAG. DAG, the directed graph part, just means references. We just point to things in a single direction. If you ever made objects that point to other objects, cool, you get directed graph. Acyclic just means that no part of this can refer back to itself, which means you also can't have a child point back up to its parent. That's an important property. And here's how that works. So anything that looks like this DAG, we can use structural sharing, and thus we can have persistent immutable version of. But say we want to make an edit. Let's edit this node. Now we can't mutate, so we actually need to make a copy of that node with the mutation applied. It can still point to its existing child. That's fine. We're not touching that child. But anything that pointed to that needs to now point to the new one. But again, no mutating, so let's make a copy. And we need to repeat this until we get to the root. And now we have a brand new structure with our mutation applied. And you can see that there's all this shared stuff, like this really simple example that I drew just to fit it on a slide. Still, more than 50% of the structure is shared. And most importantly, the previous one was completely unchanged. So I can use these both, old and new, at the same time. That's fine. That's what persistent means. And if I want, I can just let the old one get garbage collected if I lose a reference to it. But OK, this is academically interesting. I can model all my data as DAGs. But we really want arrays and objects. Every programming language has these two concepts, lists of values, key value pairs. And they're the blood that makes our applications work. So without these, without arrays and objects, just like how practical is this anyway? And if we look at the data structures that we usually use to implement arrays and objects, vectors and hash tables, they're not DAGs. Luckily for us, there's a version of a DAG called a tree. This is pronounced tree, right? Retrieve, which we can use to model lists of values and key value pairs. So there's an index tree. And an index tree, same idea. You have nodes that point to other nodes, but each node is going to be an array of a fixed size. And the values are in the leaves. So this is a list. Just like an array is a list, if you iterate through it in a depth-first traversal, you'll get all of the values of the list in exactly the order that you want them. And depth-first traversal is really fast, so the iteration here is really fast. Getting a value is also really fast. Here's how that works. So I want to get index 141. Let's look at this as a binary number. So that's 141 in binary. And what I want to do is I want to look at ranges of bits and then use those as indices into each of these nodes. So I get 1, 0, and then I fall to 0, 0, and then I fall to 1, 1, and then I fall to 0, 1, and I found my index 141. So most implementations don't use arrays with 4 elements wide. They usually use 32. It maps nice to our hardware, 32. Number should sound familiar. And with 32, you need to make even fewer hops. So the largest version of this data structure we can fit in JavaScript is 2 to the 32nd. And in that, we only ever need 8 hops. So it turns out, like bit shifting and array lookups, like JavaScript VMs are good at that. So this is really fast. OK, setting, we just use a structural sharing technique. So that same index, we want to set the value foo into it. So we put foo there. We make copies of only the things that changed. And we refer to all the things that didn't change. And now we have a brand new structure. And the original is unchanged. And we've set foo. So that's a list. We have lists of values. There's another one of these called a hash tree. This works similar to lists, but it's a little bit different. So we still have nodes that are arrays of fixed size. But we have some nodes that are leafs. They hold values. And they actually hold keys. And there's values at those keys. So same thing here. We can iterate through these using a depth-first traversal. But if you'll notice, there's not any particular order to these. So you can't expect a fixed order like you can if you iterate through the keys of a JavaScript object. And that's actually important. That enables some performance optimizations here. And we can actually beat JavaScript objects in the ES6 map in a lot of cases because of that. Now, there's one important detail. In the list, I hopped through this using a binary number, and if we're going to use keys, like strings or something, we need to turn those into a number. So in order to make this work, we need a function called hash. So if you guys have ever implemented a hash table before, something like that, you're going to be familiar with this. Anything goes in, a number has to come out. Specifically, a 32-bit number has to come out. And here's some examples of what that might look like. Let's get that up. Yeah, OK. So I can hash a string. I can hash a number. Actually, hash another list. So this is cool. Like if you guys have ever made use an object as a map and realized, like, oh, crap, I can only use strings as keys. I can use anything as keys. And there's a version of hash built into Immutable.js and really any library that will provide these kind of structures for you, so you don't have to think about that. So let's do a get. Let's get capital R. So first we need to hash R, and it turns out that that's 82. And we're going to get the binary number of 82. And we're going to do the same trick, only this time I'm going to start with the least significant bits and move forward. So I'm going to do 1, 0, 0, 0, 0, 1. And then I found a value node. So notice I didn't even have to go through the whole number. I just had to go until I found a value node. I need to check to make sure that my keys are the same. So I'm going to do a little equality check and make sure that the key matches up and I didn't get some kind of collision. And then I can return back Rob. That's what I got. And setting, same idea, structural sharing. So I get the hash. Oh shit. OK. I can't point to two things there. So how about we just move them? We'll put another node there. We'll move to the next most significant bits. And I didn't change to the previous one. I just kind of stretched out that pointer there to make visual room for this in my UI here. And then we'll wire them back up. And now I've added this thing in here. So we can deal with collisions really easily. So that's a key value map. Sweet. OK. The implementations are trees. But the interfaces that we can provide are lists and maps. And that's what we actually want to use. OK. These are not my ideas. I'm not a brilliant man. I'm a great copycat. I want to go through some badasses. This is homework. All right, everyone, write down these names. Do your research. These people are fucking awesome. JCR Licklider, he was a director of ARPA's info processing team back in 1960. And the 1960 date, that's important because it was right before ARPANET. He actually left ARPA before ARPANET started, but he wrote all the important papers that set forth the technology to do this. Also, importantly, along with one of his coworkers, invented the trie data structure. So props to him. Alan Kay, he worked at Xerox PARC. He created Smalltalk. He basically invented object-oriented programming, or at least was a strong proponent of it, and made it actually practical to use. But he has this quote. I'm going to read it because it's awesome. The last thing you want any programmer to do is mess with internal state, even if presented figuratively. It is unfortunate that much of what is called object-oriented programming today is simply old-style programming with fancier constructs. He wrote that like a decade ago, and we still have not learned from Alan Kay. Phil Bagwell, late Phil Bagwell, unfortunately, he invented the hash array mapped trie. So those are the structures I just showed you. And was generally like the coolest person ever. Go read about him. And then Rich Hickey. So Rich invented Clojure, which is a super cool language. If you haven't checked it out, you absolutely should. There's tons of really awesome ideas. And some of the talks you've heard about today are blatantly stealing ideas right out of Clojure. Another quote that I have to read for you. Simplicity is hard work, but it has a huge payoff. The person who's genuinely using a simpler system is going to be able to affect the greater amount of change with the least amount of work, and he's going to kick your ass. That's from a talk that Rich Hickey gave just a couple years ago. A must watch. OK. Why should we care about any of this? Because we'd like challenging dogma? No. We want to solve problems. We're software engineers. We want to build stuff. If this doesn't solve problems for us, we don't want to use it. So what problems does it solve? Well, usually when you hear about these things from people who are like, real computer scientists working on like hardware and stuff, not us lowly web engineers, just kidding. You hear about concurrency and how it's really hard. And if you have immutable data, you can do lock-free concurrency and you can parallelize your data. And Clojure takes advantage of this to huge effect, and it's awesome. But luckily for us JavaScripters, JavaScript's single-threaded, we don't really have to worry about this whole class of problems. And for good reason, multi-threading, there be dragons. It's a sea of awfulness. Multi-threading is hard. But for the same reason, we're in trouble. Processor speeds have increased year over year for a long time, right up until the last couple of years. And clock speeds aren't improving anymore. And actually, with the shift to mobile, they go down. And the next thing that comes after mobile will probably be even smaller, and we'll see another shift down. But the one thing that we are seeing is that those processors have multiple cores, which means more parallelism. And so if your language has native support for multithreading, you can take advantage of this stuff, which JavaScript does not. So if we embrace immutability, we might enable JavaScript's future. In a multi-threaded world, I think this is really important. Immutable.js does not solve this problem. We need to bake it deep into the language and the runtimes. But, OK, this still solves some of the problems that we have today. And I'm just going to scratch the surface. The first one I talk about is time and value and decomplecting them. So mutable objects, they complect time and value. And here's what I mean by that. There are three concepts that I want to talk about: identity, value, and time. And I'm stealing this blatantly from Rich Hickey. Identity is a thing. You know, if you close your eyes and I walk over here, and you open your eyes again, I'm still me, right? But my x-coordinate was here, and now it's here, right? Time passed, I'm me, but the value changed. I didn't edit the value. I just had a new value at a new point in time. This is a really, really important concept, because when this holds, you don't go back in time and edit things. Everyone's like, go watch Back to the Future. What happens when you go back and you edit something? Shit falls apart. Immutable data removes complexity. Immutable data, it's just like mutable data, except it has one fewer feature. You can't edit it. It is simpler. And any time that we can solve problems by making things simpler, that's a beautiful thing. So I want to talk about the many mutators problems. We call this the shared mutable state. Pete Hunt calls this the root of all evil. I agree with him. And I really think that we have mutable state Stockholm syndrome. We think that this is good for some reason. I don't get it. Why do we think this is good? This is a contrived example. Bear with me. I'm writing an NPM package, and my NPM package is called touch and print. It's going to export this function. We can pass in a function. I'm going to build up some data. I'm going to pass it to your function. And I'm going to console log some key. Super contrived, right? What promises can I make? None. Literally none. I have no fucking clue what will happen when I call this console log. And this is contrived. But it's important because we care about this problem. What changed? When we have interactive applications, we go from state A to state B. And in an effort to have highly performant applications, we want to know what changed so we can do the least amount of work to update our UI, our models, and keep everything in check. So we actually end up writing code that looks like this. We have some data store that lives in some global variable. We wrap it around with a store and call it flux, but it's still a global variable. We render it. We do some internet business with the URL, which eventually finishes. And then, who knows, it probably mutated that store. Maybe we'll get a change event, maybe we'll get a callback, and then we're going to re-render again. And we have a problem. We don't know what changed. So there are a lot of ways to solve this problem. The community is super active about this. And for a long time, we've been pitching this. This is a new feature that's going to be in ES7, not ES6, ES7. And the way I like to talk about this is, if you can't keep track of all the possible mutators, well, the least you can do is hope to observe the mutation. And here's how you use it. We're going to do the same thing, only this time we're going to observe the data store. So when the data store changes, we're going to get this neat array of the changed things that happened, and we're going to call render UI again. So now I can call load data into store, and I don't even need to worry about a callback because my object observe will call. But what do I do with that? What are these changed things? Maybe if I'm writing individual state-to-state transition code, that might be helpful. But React has taught us that that's not really the way that we want to do things. Also, what happens here? I'm going to do something expensive, like render my whole UI. And then I set 3 fields. Well, we actually don't agree yet. The spec has still not quite figured this out. We have a strong opinion on what to do here. But we could either call that 3 times, probably bad, or we could wait until the end of the frame and then call this, at which point we've added additional asynchronicity into our application, additional complexity. Also, how about this? Let's set a deep field into our data store, because they're usually, oh yeah, imagine that's this data store. Crickets, nothing will happen here. We can only observe one level of fields deep, but that's OK. We can just write a function that recurses and does object observe. So let's have observe deeply. There are libraries out there that do this. It's pretty cool. So I want to like grab a reference to something out of my data store and hold on to it. And then I'm going to like actually replace that with a new object. And I'm going to set a field on it. Oh, crap. I forgot to observe that one. And then I'm going to take my previous thing and I pass some other random part of my application. And they're going to edit it. Oh, shit. My app just re-rendered. We have to like keep track of all this stuff. Yuck. OK, dirty bits. No ES7. That's cool. Nobody has ES7 anyway. This is the way that we solve this today, right? Dirty bits. Scandalous extra bits. They're going to keep track of where our data is dirty and where it's not. So we have some like underlying raw data store. And we're just going to have getters and setters. So the getter is just going to pull out of the raw data store. The setters is going to set into the raw data store, but it's going to flip this flag. And when we render, first we're going to check. If it's not dirty, we can just bail. You don't have to do anything. Otherwise, we're going to flip the dirty flag back, and we're going to do our work. And this is cool. Like no op, no op, no op. Set some stuff. Updated UI. Sweet. Problem solved. Until we do this. Whoops. When we call the second one, the first one set the dirty flag back. But like, OK, we can solve this. We'll just write a framework that encapsulates all of this pattern and like not let you do this. But that couples our model classes to our view classes. Why do we want to do that? I just want to use like plain JavaScript objects. Why do I have to write specific model classes to couple to my view classes? This is something that React teaches us we don't have to do. People are like, oh, don't worry, it's just a V and MVC. Well, that's because like, you don't need an M because we have arrays and objects. So I posit that immutable change tracking actually solves this problem, and it does it extremely performantly. Here's how that works. So this is an example from Immutable again. I want to make a map, an immutable map, with a key-value pair. And I'm going to set that key to foo and get a new map. I'm going to compare them, different objects. Returns false. Cool, something changed. OK, back to that first map, which didn't change. Right? I'm going to set key to value. It's going to figure out, like, oh, that already was value. So it's going to no op. It's going to return itself. I compare them. It's true. Cool. Nothing changed. That's the whole demo. All right, let's do it for deep structures, because, OK, deep structures were hard, right? So here's a map of maps. Right? Foo and bar each have a value to key. So I want to do the set in. So one tricky bit with immutable structures is when you want to mutate them. Previously, we just like work our way down and like futz around and then get out of there. But now we actually have to be really explicit about the change we want to make. So we want to crawl into foo, val, and then set that to 500. So of course, that's going to result in a whole new map of maps. So we expect that to be false. And if we get foo from both the new one and the old one, we expect that to return false because we've edited that. But if we reach in and get bar, it's true because we just recycled it. So the whole thing did change from the top. But as soon as we get to a leaf that hasn't changed, we can detect it with reference equality, which is free. OK, I want to talk about memoization. You guys have heard of this super powerful optimization technique. Let's say I have some expensive function. I'm going to reduce the list and add all the items together and get a sum. And I want to memoize that, because that might be expensive when I have 1 million elements, and I'm going to sum those. This is what I want. And I looked on the internet for a memoize function for JavaScript, and this was the one that had like the most votes on Stack Overflow. What the fuck is that? That's an O of n operation sitting in our memoize function? And a slow one? So I ran this, and it turns out that for my 1 million elements sum, that it's more expensive to memoize it than it's not. Here's a new version. OK, I dumbed it down a little bit, and I'm only memoizing the previous call, not all calls. But you can imagine I could use a map or something. But all I want to do is like check the previous arg. If it was the same, then I could just return the previous result. Otherwise, I'm going to store the previous arg, run the function, and return the previous result. So I do this. It's like, OK, it's expensive. Do it the second time. Sweet, it's free. Then I push onto my array. Uh-oh. Right, it was the same array. I can't push into it and expect this equality check to work, because, of course, it's the same array. So that doesn't work. So let's replace it with a mutable list. So I have a list of 1 million elements instead. I'm going to sum them. And the second one is free. Cool. By the way, same implementation of memoize. Haven't changed anything. Now I'm going to push into my list. I'm going to get a new list. I'm going to call sum. Sweet, it works. That was easy. This is relevant because in React, we have this thing called should component update. I picked out change tracking and memoization specifically because those are the two things that we've been trying to figure out for the last decade to make our apps fast. Should component update is a hook that Jason talked about yesterday. So I'm going to flip through this really fast. The default implementation is return true. Why? Well, JavaScript's full of mutable objects. And we can't do, for the same reason that I was showing before, we want to memoize. But it would be sweet if we could do this. And Jason showed you guys how this works. Shallow equal, by the way, is implemented something like this. I shortened it a little bit. But here's the important part. Reference equality. That's why we can't use mutable stuff. And we wrapped this up for you. Jason told you about that. I want to pimp a little bit here. This is David's project that pulls React into ClojureScript, which I'm a huge fan of. And it's faster than React. And everyone's like, wait, how can you wrap React and then be faster? Well, all data in ClojureScript is immutable. And immutable data is faster to compare than mutable data. So he just turns on that memoization optimization by default. And then everything is faster right out of the box. So reconciliation is pretty damn fast, right? But if it's deep enough, it can be slower than persistent data. Reconciliation is an O of n problem. Reconciliation, where you can cut off all the legs that you definitely know haven't changed, turns it into a O log n problem, which is a big deal. Immutable data is a constant factor slower, right? 3 to 5 times slower. Maybe depends on your implementation. If I have to pay a constant time penalty on my push operation to turn an O of n problem to an O of log n problem, hell yes. All right, now I want to talk about Flux. Flux is an awesome pattern for structuring an application, but I have one gripe with it. The stores usually contain mutable data. When you get an action, you handle it by munging around with your internal state. You fire off a change event. And what are we supposed to do, right? A lot of people have asked me this question. When I get this change event at the top of my application, how am I supposed to make that fast? I have to re-render my whole app? Well, if my app is big, it's got to be slow. Am I supposed to thread change events only down to individual bits and pieces and just have those update? That seems wrong. I'm like, yeah. Reconciliation is pretty damn fast, but maybe there's a better way. So I'm going to use our favorite Hello World app to do MVC. And I pulled this straight out of the one that Pete Hunt wrote. And we're going to focus on the create action, and specifically this problem right here. We're going to use an object as to-dos, and we're going to mutate it when we get a new to-do. Well, what happens when we add a new to-do? We're going to add a to-do here, and we're going to reconcile, right? We're going to reconcile through our whole app, only to find that the only thing that changed was we added one thing on the end. So that was a lot of work. Now, if we add pure render mixin, we solve this problem, right? But only if we add immutable data. So let's build Flux stores with immutable data. I'm going to do this inline. We're going to live keynote code edit right here. So people keep asking me this question. Immutable.js is awesome, but I want to use it with Flux. Do I need to go get a whole new Flux library? No. This is really easy. OK, to-dos, I'm going to replace that with an ordered map. Ordered map because the order in which you add keys into it will dictate the order in which they come out when you iterate, which is the same behavior as a JavaScript object. Now I'm going to change each to-do into a map of keys to values instead of a JavaScript object. And I'm going to call to-dos.set, which is going to return me a new to-dos. And then I'm going to stick pure render mixin everywhere. That's it. I just put immutable data in my Flux. So now, when I add a new to-do, reconcile looks like that. Should component update is really fast, and it skips all the way to the end. It's like, you're the thing that changed. Cool. So Flux store is the identity. The Flux store is global, and it doesn't, it's the same store over time. But the value within your Flux store should be an immutable value. And as time passes through your application, it should hold new immutable values. This is the same thing I was talking before. So Flux models this really well. All right, I'm going to do a bonus because I have one more minute, which is more time than I need to undo. OK, here's where we were. I'm going to add undo to Flux. First, and here's how this works. OK, every time I edit to-dos, the previous one was unedited, right? So all I need to do is hold on to all of the ones that I've had before. So I'm going to make something called history. I'm just going to use a regular mutable array. For now, it's not that big of a deal, actually. And right before I do an edit, I'm going to push into my history. And now I have a history of every change that's ever happened. So I can add a new action called undo. And if my history has stuff in it, then I'm going to pop out and assign that to to-dos. Oh, I should have added a to-do store.emit change. Imagine that's in there too. Gotta tell everyone something changed. And that's it. That's undo. Cool. Now we've got undo. That's literally it. OK. So we've learned persistent immutable data structures. They're pretty damn interesting. They can enable a lot of cool stuff for us. They work. They're efficient because of structural sharing, which gives them very little overhead, constant time overhead in time, and log n overhead on memory. And garbage collection cleans up after us if we let go of them. We want no more mutable state Stockholm syndrome. Stop telling yourself this is a good idea. We can solve problems by removing complexity, not by adding it. And that's pretty awesome. I don't have time for questions, but if you have a question, tweet me or come find me. I'll be around the rest of the day. Thanks, guys.